In the last class, we have discussed about crystals. Today, we are going to discuss symmetry in crystals or crystal symmetry. What is symmetry and why this symmetry in crystals are very important? Because many of the physical properties of crystals are mainly depends on its symmetry, and if ionic crystal or metallic crystal, if you are doping in crystals, everywhere you can see that how the symmetry varies, or is there any deviation in its symmetry, then its physical property varies. What is symmetry? What is crystal symmetry? Which describes definite ordered arrangements of faces and edges of a crystal. Crystals possess different symmetries or symmetry elements. What is symmetry elements? How important these symmetry elements when we are discussing about crystals or crystallography? Symmetry operation. What is symmetry operation? We can see that symmetry in a crystal means by certain operation the geometry of the crystal observed invariant, or we can see it is an operation performed on an object or pattern which brings it into a position which is absolutely indistinguishable from the old position. When we discuss about the details of this symmetry operation, point group operation and space group symmetry operation, these are the two symmetry operations mainly we are considering. First one is point group symmetry operation. Symmetry operation performed about a point or line, then we call it is point symmetry operation. In space group symmetry operation, symmetry operation performed by translation as well as rotation. So, these are the two main types of symmetry operation. When we see a crystal and rotates or reflection, after certain time we observe that particular crystal will be observed in the previous manner itself. So, we can see if in a human body, if you are placing a mirror like this, then you can see if you are looking this side, then we can see the reflection of this part is similar to this part, almost similar to this part, then we can see the full human being or full image of mine is similar when you are placing a mirror like this or in opposite way. So, this is a one type of symmetry we are going to discuss. First one, point group symmetry elements exhibited by crystals. First one is centrosymmetry or inversion center, then reflection symmetry, then rotation symmetry. When we look into a crystal, because in the last class we discussed 7 crystal systems. In that 7 crystal systems, the cubic crystal is we can discuss, because when theoretically we are explaining, cubic crystal is one of the very simple as well as it shows very important symmetry when we rotates or we are taking reflections plane, or reflection plane in many ways we can take. So, there are 23 symmetry elements in a cubic crystal, where we can see one is first one we consider center of symmetry or inversion center. If you look at this particular pattern, here this is a cube, and in this cube there are 1, 2, 3, 4 planes and 2 opposite planes, total 6 faces are here, and if you are placing a axis here and rotates about 90 degree, the particular geometry is indistinguishable. It means that it is invariant, it is similar, we cannot say is there any variation is happened on this particular geometry. So, this particular thing is an axis, but when we look into the center of this particular cube, you can see along this center, in this center we can rotate, or this particular center is called center of symmetry. Along that center we can rotate this particular cube and crystal sees invariant, or its geometrical or its faces are invariant in this particular manner. So, here crystal possesses an inversion center if every lattice point given by position vector r. If you are taking a particular distance from the center towards in this direction, if you are taken as r, then similarly from this particular point there is an opposite direction. If you are taking that particular vector is minus r, then these particular things are very important when we are discussing about the crystal symmetry. The central line at equal distance from various symmetrical positions are also important of discussing the symmetry of the crystal. Then reflection symmetry. In this particular case, reflection symmetry means, I already discussed that if you are keeping a mirror like this part you can see in the mirror, means that full cube you can see when you are looking from the side of the mirror, the total cube you can see in the mirror. So, means that this half is the real reflection of this part, and it is similar to this particular part when you are keeping your mirror like this, and if you are keeping your mirror in opposite way, then also you can see this reflection in this side. It is also very important when we are discussing the plane of symmetry or mirror symmetry. Here we look in this particular figure, you can see reflection symmetry or plane of symmetry. A crystal is said to have a plane of symmetry when it is divided an imaginary plane into two halves, such that one is the mirror image of the other. Crystal is left unchanged in every way after being reflected by the plane. So, when we look into this particular figure, here we can see three plane of symmetry parallel to the faces, three plane of symmetry parallel to the faces. In this cube you can cut like this, and also you can cut like this. These are the two main thing, and here like this, here like this. Similarly, you can cut in this way also. So, there are three planes of symmetry parallel to the faces. Similarly, here you can see the diagonal way. In this figure you can see in this diagonal way also you can cut, then also we can see mirror images on the opposite side. So, 6 diagonal planes of symmetry for this particular crystal, that is clearly you can see in this particular figures, or in these figures you can clearly see 6 diagonal planes like this one, like this one, like this one, or in this way also you can see. All these are the totally 6 plus 3 9 symmetries are there, in this 9 plane of symmetries of the cube are there. Next one is axis of symmetry or rotation symmetry. I already shown for showing center of symmetry. Here in this particular cube there are points, or we can place an axis of symmetry or rotation axis of symmetry here, and if you rotates this particular model, a body possesses rotation symmetry about an axis if after rotation of the body about this axis by some angle phi, the body remains invariant, which means that after certain operation, here operation is rotation. When this particular cube is placed like this and rotate about 90 degree, then the similar model we can observe. There is no change in the geometry of this particular thing. The axis is called, this particular axis you call n-fold axis if the angle of rotation is 360 by n. Here total rotation 360 degree and number of rotation you can place here n type of rotation. If it is 90 degree, or we can see 360 by n, if n is n-fold axis, if the angle of rotation is 360 by n, then if the equivalent configuration occurs after rotation of 180 degree, 120 degree, 90 degree, the axis of rotation are known as two-fold if the rotation is 180 degree, and if the rotation is 120 degree, of course 360 by 120 you can see it is 3, then it is called three-fold, and if it is 90 degree, 360 by 90 degree you can see that is 4. So, that particular rotation is called four-fold. So, these type of rotation along an axis of particular geometry, if it is 180 degree we call two-fold axis of symmetry, and 120 degree rotation the same specimen is invariant, then that particular symmetry, that particular axis of symmetry is called three-fold, and if it is repeats, the geometry repeats after 90 degree, then called four-fold axis of symmetry. That we can see here in this first one, this is 90 degree, that is again 90 degree. So, we can see this is the this particular is called four-fold axis of symmetry. How many four-fold axis of symmetry for a cube? You can see this is one, similarly here is second one, and here is another axis. So, there are three four-fold axis of symmetry for a cube. So, which means that 4 times during a complete revolution, that is 90 degree is 360 by n. So, n is 4, which means that four-fold symmetry or this particular axis is called tetrad axis. Cube possesses 3 tetrad axis. This is cube, here this one is one axis and another one is like this, and another one is in this way. These are the 3 tetrad axes which a cube possesses. We can see if a cube rotates about body diagonal through. Body diagonal through means this particular corner. In this corner, if you place an axis like this and rotates. So, if you rotates this particular 120 degree, then you can see that this particular geometry is invariant, which means that after 120 degree of rotation along this particular axis, along this particular axis, this particular specimen looks invariant, which means that this also a axis of symmetry. That particular axis of symmetry happened, or repetition of the geometry happened, or after 120 degree of rotation it achieved itself. So, this particular fold is called three-fold symmetry, that is three-fold symmetry, and this how many number of these type of axis for a particular cube, which means that there are one axis like this. So, there are 8 corners for a cube. So, 8 corners means here one corner and 2 corner. So, there are 4 such axes you can make to this particular cube. So, we can see that a threefold symmetry, or we can see these particular axes are triad axis. Cube possesses these type of 4 triad axes. One is like this, and second one is along this, and third one and this one. Totally 4 axes are there. Cube possesses 4 triad axis. Now, what happened when this n, if n is 2? In the previous case n is 3, here when we take n is 2, the crystal has to be rotated through an angle 180 degree. If n is 1, then we can see if n is 1 only identical. So, the crystal has to be rotated, about an axis, achieve self coincidence after 360 degree rotation, that is identity. So, that is for every crystal that type of identity is there for 360 degree. But in the case of 180 degree, in previous case you already see that if n is equal to 2, then 180 degree, then you can see two-fold axis. Here this is n, if n is equal to 2, the crystal has to be rotated through an angle of 180 degree about an axis, achieve itself after this particular rotation, here this one 180 degree. Then achieve self coincidence after 180 degrees of rotation, that is this particular axis is one such axis. Here also this along this edges another axis. So, these type of we can see there are two-fold symmetry or dyad axis. A cube possesses how many edges? Here 4 edges, and here also 4 edges are there, 8 edges are there, and if you are placing here an axis like this, and here also axis, and so when you rotate 180 degree, there are repetition of this particular specimen itself, and that particular axis called dyad axis. For a cube possesses 6 dyad axis. So, when you look into these all, if any possibility of 5-fold axis for a cube, 5-fold axis of symmetry for any other symmetry, you can see any other symmetry greater than 5 is there, or greater than 6 is there, or 7 is there, that is another question. Now, everybody is discussing if there is a possibility of 7-fold axis there in a crystal. Of course, there are certain discussions are going on. Can we see a 5-fold symmetry? Of course, some crystals like quasi crystals, they are possessing some 5-fold symmetry, but of course, they are in the beginning and discussions, and some people are mainly discussing about 5-fold symmetry and 7-fold symmetry, etc. But so common crystallography, now also we are mainly dealing about these type of axis of symmetries. Of course, symmetry axis higher than 6 are not at all discussing. Now, why these 5-fold symmetry and 7-fold symmetry are not possible? We already discussed crystal is a regular periodic arrangements of atoms or molecules, and these arrangements of atoms or molecules are in 3-dimensional, then only a perfect crystal arises. If these arrangements are throughout a specimen, then only it is single crystalline. If some impurities or defects, etc. are coming in the crystal, its property or physical property varies. mainly the properties like optical properties. When in the ion or atom disturb the regular arrangements, or maybe due to the presence of some ions other than its own atoms or molecules, then if that particular or impurity, we can call that particular is dopant or impurity, that impurity disturbance or make some disturbances in the symmetry. In that way, the physical property like optical absorption, optical emission, etc. may be varies. That is why the symmetry in a crystal is more and more important when we discussing electrical property, optical property, luminescence, phosphorescence. In that case, we have to observe more about the crystal symmetry. And also when we take the scattering, another important thing is electromagnetic waves are scattered by crystal structures. This scattering also depends upon how the lattice are perfect. If any the lattices are symmetric, if any deviation from its symmetry, that also induces some variation in the regular property or physical property of that material. So, that is why now also different type of materials having variation in symmetry, fivefold symmetry is there. In some cases its electrical property as well as the phonon scattering etc. in the material is drastically varies compared to its ideal one crystal. If an ideal crystal means all the atoms are arranged or it is possessed in its regular position. So, there is no variation in that particular position is happened. That is why symmetry is more important when deals with the crystallography. So, here when we discuss in this here symmetrical elements of a cube, I already discussed. There are center of symmetry, that is only one center of symmetry. Center of symmetry of a crystal is 1. That is, this particular structure is cube, cube has only 1. Then plane of symmetry, we already shown plane of symmetry of a cube is equal to 9 plane of symmetry. And how many dyad axis of a dyad axis of symmetry, that is dyad axis. How many dyad axis? 6 dyad axis already we discussed. Now, how many number of triad axis? Triad axis means after certain rotation 120-degree rotation the crystal repeats itself. Then how many number of these after 120-degree these types of 4 triad axis, and how many number of dyad axis? Sorry, not dyad axis, here we already discussed dyad axis, tetrad axis. Tetrad axis. In this tetrad axis 90-degree after 90-degree axis of rotation or rotation of 90-degree the crystal repeats itself. These type of 3 tetrad axis. So, this specimen you can see 9 plus 1 10, 10 plus 6 16, plus 4 20 and plus 3 23. So, there are 23 symmetry elements when we are considering the specimen is a cube. Thus, the total number of symmetry axis of a cube structure is 23. So, we can see these many materials are crystallized in cubic, mainly there are simple cubic, body centered cubic, face centered cubic. In these structures, these all symmetry elements we can observe in one way or other. Now, the symmetry, here we have already discussed about an axis or a point, that is point symmetry. Now, translational symmetry elements. What is translational symmetry elements? So, translational symmetry elements are, one is glide planes and second one is screw axis. Glide planes and screw axis. Glide planes. Second one is screw axis. From this itself we can see what is glide plane, and second one is screw axis. These are the two types of things happen when we look into crystal. A glide plane is a reflection followed by translation in a direction parallel to the plane. At the same time, screw axis, rotation axis coupled with a translation parallel to the rotation axis will give rise to new symmetry elements called screw axis, and screw axis symbol is commonly taken as n, that is n suffix m. When rotation of 2 pi by n, 2 pi by n means 360 by n, a translation of m by n times the translational vector parallel to the rotation axis. For an example, if you see 4 2, here n is 4 and m is 2, rotate point through 90 degree about the symmetric axis and translate the point by 2 by 4, means that 2 by 4 is equal to 1 by 2 times the translation vector parallel to the rotation axis. Now, space group. Space group. In the space group, combination of point group symmetry with the translation symmetry elements are called space group. Crystal exhibit 230 space group, that is 230 unique combination of 3-dimensional symmetry. They are. Now, based on this we can make Bravais space lattices. Bravais space lattices. In this Bravais space lattices, all atoms are of same kind, all lattice points are equivalent. But when we consider non-Bravais lattice, atoms can be of different kind, some lattice points are not equivalent. A combination of 2 or more Bravais lattice also we can see in non-Bravais lattice. So, crystal lattice are mainly classified into two, they are Bravais lattice and non-Bravais lattices. Here also the symmetry and symmetry are based on this symmetry only we are considering the Bravais lattices. These Bravais lattices are actually come into picture in 1848. Bravais showed that there are only 14 different arrangements or arrays of network of lattices which are in 3 dimension, in which points can be arranged in space so that each point has identical surroundings. There are, or these are called Bravais lattice. Space lattices, that is the arrangement and orientation which looks exactly the same at each point. So, that type of 3 dimensional geometry can be called as Bravais lattice, which are 3 dimensional. So, based on this, we considering the how many number of Bravais lattice we can observe in all 7 crystal systems, that are they are 14 Bravais lattices, cubic, that is 3 type of cubic Bravais lattices are there. They are body centered, simple cubic and face centered cubic. Similarly, tetragonal. In the case of tetragonal, number of Bravais lattices are only 2. In the orthorhombic cases, there are 4 number of Bravais lattices, and in the case of rhombohedral, only 1. Monoclinic, you can see 2 types, and triclinic 1, hexagonal only 1. So, there are in the case of this the hexagonal structure, in this all we can see only 1 type of Bravais lattice. So, these are the main 14, or we can see only 14 Bravais lattices we can observe in crystal. So, first one is cubic. In this cubic, you can see simple cubic, I already discussed simple cubic, body centered cubic and face centered cubic. In tetragonal, 2 Bravais lattices are there, they are simple tetragonal and body centered tetragonal, and orthorhombic, 4 orthorhombic structures are there. First one is simple orthorhombic, then body centered, there may be an atom or molecule in the body center of course. Then face center, all the faces are having 1 atom or molecule, they are face centered, and base centered. Base centered means in this particular structure, top and bottom are having 1 atom or molecule. So, that is base centered. So, these are the 4 Bravais lattice in the case of orthorhombic structures. In rhombohedral structure, in this particular structure we can see only 1 type of Bravais lattice, only 1 Bravais lattice. In the case of monoclinic, there are 2, one is simple monoclinic. This is the monoclinic structure. In this structure, we can see only simple cubic, and similarly here and here 1 atom or molecule sits, then that type of structure is called base centered, and simple monoclinic and base centered. So, 2 type of monoclinic Bravais lattices, and triclinic also. In triclinic, only 1 Bravais lattice, and in hexagonal case I already discussed only 1. These are the main structures that we observed. Now, based on these particular things, symmetry, associated axis, rotation, etc., based on this we classified crystal 3 dimensional crystals. Now, some structures, crystal structures, metallic crystal structure. Most of the metals are crystalline. We observe aluminum, gold, copper, these are very important material. We are using these materials for different application. The copper is very good conductor of electricity, aluminum good conductor of electricity, and heat also. These particular materials are crystallized. Nature gives in the crystalline form, maybe in polycrystalline, and by making single crystalline we can make these particular polycrystalline material into single crystalline. So, most of the metals are taking or digging from the or purification. By purification we are getting copper getting in the form of a crystalline structure. So, when the hard sphere model for the representation of a crystal structure, each sphere represents an ion core. So, when we discuss about metallic structure, 3 simple crystal structures are found for most of the common metals. First one is body centered cubic. Many metallic elements we are getting is in cubic structure like copper, body centered cubic, and second one we are observing the crystals which are in face centered cubic, lead like materials, zinc like elements or metals are getting like hexagonal close packed or hexagonal structures. So, cubic crystal systems are there, body centered cubic crystals are there, and face centered cubic crystals are there. All these structures are observed in metals mainly. And of course, face centered cubic we already discussed, sodium chloride is a very good ionic crystal, and it is crystallizes in the form of face centered cubic. At the same time, when we look into diamond there are a particular structure, diamond structure. Here this is a diamond structure, the unit cell of a diamond. Here also we can see a structure, there are in the all the faces are containing half of this atom, means that one atom is on the faces of these 6 faces, and at the same time you can see in the 1/4 and 3/4 there are 1 atom seats. So, this particular structure is diamond structure. Of course, it is also cubic, metals in the cubic form, diamond also cubic form, but a speciality in there, due to that it is called a particular structure, it is diamond structure. Silicon and germanium are also crystallized in these diamond structures. And another important thing when we look here, coordination number, important structure when we are discussing based on crystallography. First one is coordination number of equidistant nearest neighbors that an atom has in the given structure. So, we can look into this particular picture. If an atom is here, which one is very near to this, or here also we can see which one is very near to this. Here you can see this one and this one. So, these are the how many number of that type of nearest neighbors are there, because attraction and repulsion and many interactions between these atoms are happening. So, nearest neighbors are very important when we are discussing the crystal structure. So, nearest neighbor distances, or most of the time nearest neighbor distance are commonly called 2r, that is the distance between the center of 2 nearest neighboring atom, center of the 2 nearest neighboring atom. So, means that one atom has a radius of r, then 2 atoms are there, r plus r. So, that distance is 2r. So, it is called 2r. And another important term when we discuss the crystal structure is atomic radius. Atomic radius r, half the distance between nearest neighbors in crystalline solid without impurity, means that if an impurity is there, that is situated maybe in the vacancy position in the crystal, or may be located in the interstitial position of the crystal. So, if it is in the interstitial position of the crystal or in the vacancy position, it affects the distance between the nearest. So, we cannot consider that when discussing the nearest neighbor distance, calculating the nearest neighbor distance. Another parameter is atomic packing factor, or commonly we call APF. Fraction of space occupied atoms in a unit cell, it is the ratio of the volume of the atoms occupying the unit cell to the volume of the unit cell. So, that particular is called atomic packing fraction. When we look into simple cubic structure, effective number of lattice points per cell is 8 into 1 by 8, that is 8 corners are for a simple cubic, and all the corners possess 1 by 8 of an atom, or we call effective number of lattice points per cell is 8 into 1 by 8, that is 1. Similarly, coordination number we can calculate already, that is 6 for a cube, and nearest neighbor distance 2r, that 2r is called commonly called, it is 2r can be considered as A. So, that is another important parameter. And atomic radius, commonly atomic radius is the half of the atomic radius is commonly r, that is of course half of the A or 0.5 A, and then atomic packing fraction or APF is observed in cubic structures, that is nearly 0.62. So, that is given in the APF is equal to how calculated are given by an equation shown here. In the case of body centered cubic BCC structure, body centered cubic is commonly called BCC. In the BCC structure, in the body of that particular crystal there may be an atom. So, there also calculation by calculation we can attain a value atomic packing fraction, say in the similar way we calculated there, but body centered cases coordination number is 8 and effective number of lattice points per cell is 1 by 8 into 8, because all the corners contain 1 by 8 of an atom, and number of corners are 8, 8 into 1 by 8 is 1, plus in the body center there is a full atom. So, 1 plus 1 2. So, the effective number of lattice points per cell is 2 in the case of body centered. In the case of simple cubic we already said that is only 1 by 8 into 8. In the coordination number in this case is 8 and nearest neighbor distance is 2r, that is 0.√3 A by 2. Atomic radius r is equal to, of course, that is also because in the corner, that is also that is √3 A by 4, and atomic packing fraction here we calculated as 0.68. These parameters are important when we are placing impurities inside these structures, or we modify the structures, or by placing certain kind of doping elements or ions or impurities, which means that we already know in silicon like semiconductors we are doping by bismuth or antimony, similarly boron. At that time we can observe that there is a deviation in this particular thing or distance. Of course, that depends upon the property of the material. When face centered cubic, in the case of face centered cubic structure, I already shown face centered cubic. This is a pattern face center, because you can see here one face center an atom is there. Similarly, this face, all the 6 faces are having an atom. So, these type of structures are when packed together and making a big huge crystal or single crystal, then we see that effective number of lattice points per cell, that is all the corners, of course. here also all the corners are having atom, that is you look at here, it is only 1/8 part of a atom. So, that is why we call 1/8 into 8, that is totally we can see a full atom, or maybe if you are taking a molecule at the lattice point, molecule maybe. Of course, effective number of lattice points per cell is 1, all the corners, and then of course 6 faces are containing half, 6 into half, that is 3. So, total number of effective number of lattice points. So, lattice points means here lattice points, lattice plus basis is crystal structure, basis means group of atoms or atom attached to that particular lattice point. So, here the total number of lattice points per cell is how many? It is 4. Coordination number, of course, I already discussed what is coordination number, it is 12, and nearest neighbor distance is 2r, that is root 2 a by 2, and atomic radius r, of course, atomic radius already we know, that is square root of 2 a is by 4, then atomic packing fraction APF for this particular structure is 0.74. So, this in the case of face centered cubic structures. Now, these are the simple structures similarly in the case of hexagonal close packing. In the hexagonal close packing, the effective number of lattice points per cell is, you can see this is a hexagonal structure. In this hexagonal structure, we can see there are 3 plus 3 6, and in the center 1 atom, 1 lattice point of course, and here also same thing, and many crystals like lead or zinc are crystallized in this particular structure. Effective number of lattice points per cell is 12 into 1/6, that is top and bottom, plus 2 into half. Half means here you can see this part is this half part is here, and the next half part is shared with the other face. So, that is 2 into half, that is 1, and if any mid plane are there, that is 3 mid plane may be in this particular structure. Here it is not showing, but of course, in real cases it is also there, it is like this attachment. So, there are totally 12 into 1/6 plus 2 into half plus 3, total is 6. So, effective number of lattice points per cell in the case of a hexagonal structure is 6, and coordination number is of course 12, and nearest neighbor distance, that 2r distance is a, and c by a, here this distance is a and this is the distance c, and c by a is square root of 8 by 3, that is equal to a by 3, that is nearly equal to atomic packing fraction is calculated, and it may be equal to 0.74. So, the structure, when we look into these type of crystals, different structure we can see in different materials. Simple cubic structure, mainly polonium is simple cubic, one example, and face centered cubic commonly crystallized aluminum, nickel, copper, gold, silver, lead, they are commonly crystallized in face centered cubic, and body centered cubic they are chromium, tungsten, where then alpha iron, then molybdenum, vanadium, lithium, sodium, potassium, these are crystallizes naturally crystallized in the form of body centered. And I already discussed you hexagonal close packing, magnesium, zinc, cadmium, they are commonly crystallized. Lead is crystallized in face centered cubic, but magnesium, zinc, cadmium are commonly observing in hexagonal close packing structures. Sodium chloride, of course, we already discussed. For sodium chloride is one of the very interesting and this particular material is academically very much interested to calculate many parameters. So, it is commonly crystallized in face-ended cubic. There are so many parameters associated with this sodium and chlorine, where the sodium atom is located, where the chlorine atom is located. Based on this, another simple structure is diamond. Diamond is of course it is cubic, but it is a special FCC structure. The difference is not exactly similar to that of sodium chloride, its deviation is there, that also I shown you. Then of course, many compounds are crystallized in different forms. Zinc sulphide, commonly called zinc blende structure. It is also in a particular structure, face-ended cubic structures. Then these crystallographic or symbol structures are very much important when we discuss about the property and how to modify these physical properties of the material. Another important thing in the crystallography is crystallographic direction or and the crystal planes. Here you can see this is a cubic crystal. In this cubic crystal you can see a plane, this red color structure, you can see that a triangle like this, and this triangle touches at this particular axis. If you are taking this A or this B and this C, so here all the points, one point here, one point here, one point here, that distance we taken as from this axis it is 1, from this axis it is 1, from this axis it is 1. So, this particular plane is called 1 1 plane. So, this is a 1 1 plane. So, when we are discussing how a crystal gets vibrates or crystal planes gets vibrates and in which directions the phonons are moving, etc. In that case we take it is the vibration happened along along a plane, that is in 1 1 plane, or similarly if one of the plane is not touches this plane is not touches any of the axis, then that particular plane does not contain that particular value, axis value. So, maybe if the z axis it will not touch us, then we call all the other two planes are only touching, other two axes are only touching, then it is called 1 1 0 plane. So, 1 1 0 plane, here you can see this particular plane, this particular plane is touching only these two axes. So, that two axes are we can see x or y or a or b, then that particular plane we call it will not touch us this one, then this particular plane is called 1 1 0. So, this diagonal plane, these two diagonal plane is 1 1 0 plane, but here all these three corners touches. So, this plane is 1 1 plane, that is the difference of two planes. So, that is why these planes are important. And crystallographic direction, another how important this crystallographic direction is there, how can you choose this particular direction in steps. First, choose a vector of convenient length, that length may be a or sometimes people call x. Obtain a vector projection on each of 3 axes x, y, z for direction to be drawn if necessary. Then third step is divide the 3 numbers by a common factor if the indices are to be assigned to reduce to the smallest integer value. So, and these particular values we are placing in a square bracket. So, its plane is 1 1 0 or 1 1 1 or 0 1 0 etc. So, coordinates of the final point, coordinates of the initial point reduced to smallest integer values are very important when we are considering the planes. We are not put 1 half 1, 1 1 by 3 1, we will not place only a full number, that full number is placed in a bracket, in a square bracket. So, that is why plane analysis are taking. These plane analysis are very important when we study the X-ray diffraction patterns. So, X-ray diffraction is the main experimental technique to analyze the structure of a crystal. There crystallographic planes are mentioning by Miller indices, that is another thing. Previously we see the real planes, but Miller indices is actually how X-rays sees the crystal. X-rays are seeing, how these X-rays are seeing the crystal means crystals are just like a grating element in the case of an X-ray. When X-ray incident on the grating, you are getting diffraction pattern. Similar way is similarly in Miller indices or Miller analysis, the crystal lattice may be regarded as made up of an aggregate of set of parallel equidistant planes passing through the lattice points, which is known as lattice planes. Miller evolved a method to designate a set of parallel planes in a crystal by the numbers HKL, known as Miller indices. In this session, we have discussed the symmetry in crystals, space group, point groups, and also the planes in crystals, and how the properties of crystals are depends upon the symmetry. I hope that this session is very useful to you. Thank you for watching. Goodbye.